This is Math 432, Applied Combinatorics, and I am Professor Asaf. The problem that we're going to think about for the next few videos is the following. Given a pair of fair dice, what is the probability of rolling doubles? Well, I didn't do it this time, so that's 1 trial, 2 trials, 3 trials. It seems unlikely. 4 trials. Aha! On the 5th trial, ironically, I got 5s. The question is, how long did I expect it would take me to get doubles? How often am I going to get doubles? And a lot of the so-called paradoxes that we see in combinatorics come from people not quite understanding these discrete probabilities. So let's think about how we would analyze this question from a counting point of view. We can just count how many different outcomes there are, and then we can count how many different coincidences there are. Coincidence when we get the doubles. So we can think about, we've got the 2 dice. So we've got orange and green. And we know that the orange can come up 1, 2, 3, 4, 5, or 6, each with equal likelihood. That's what I mean by a fair die. And of course, green can come up 1, 2, 3, 4, 5, 6. Now, the total number of possible rolls that I could have, right? How many rolls? Well, how many doubles are there? Well, there are 6 doubles that I could get, one corresponding to each of the numbers that I have here. But how many different outcomes could I have when I roll the dice? Well, there's 6 options for the orange, and there's 6 options for the green, and these 2 are independent, right? So there are 36 possible rolls, right? One of 6 numbers on the orange times one of 6 numbers on the green. So that means that the chance of getting doubles is about 1/6. So that means that about 1 in every 6 times I roll a pair of dice, I'm going to expect maybe I'll get a double. And as we saw in the single trial that we did, you should never base your information based on such low numbers, but based on the single trial, I got it in 5, which is pretty close to what we might think would happen. Okay, so that's the setup for the problem. But really it's a setup for the next topic that we're going to be discussing, which is discrete probability. So this is not like probability you've done if you've taken Math 408. This is going to be all of our sets are finite. And that's what we mean by the discrete probability. There's no measure theory here. I'm thinking about a finite set A of possible outcomes. And the examples here that I have, or the possible outcomes I had, were in this example, A is going to equal the set of pairs where I get, say, A, B, the 2 numbers on my dice, such that A is equal to 1 up to 6, and B is also 1 up to 6. This is my finite set of outcomes, the ordered pairs that I could get of an orange and a green die. Okay, so what's X? X is the events that I want to know how likely is that event to happen. So from our probability over here, we see that we were asking when we roll doubles. So in this case, X is going to be the set of pairs that are diagonally symmetric. So these are going to be the pairs A, A. Such that A equals 1 up to 6. And so now we can see that, okay, our counting here exactly worked out just like this. We said the number of things in the set X, that's the number of doubles that we have here, divided by the total number of rolls that we could have, which in this case is 36. So what we get is exactly the probability of the set X occurring, giving all of these possible outcomes A. It's a really simple idea. We're just counting and we're just looking at a fraction. Now, probabilities, of course, and this is something that's really important to know so that you don't say anything mathematically offensive, but the probability of X is always going to be a number between, speaking of that, between 1 and 0. So a probability of 0 means it's impossible. And we saw this was an interesting idea that we played with when we were looking at the example from the last set of videos when we were looking at the probabilistic method. And this is determined. This is definitely going to happen. So your probability is somewhere between 0 and 1. So the bigger it is, the closer to 1 it is, the more likely it is to happen, and the smaller it is, the less likely it is to happen. Let's just look at one more example. And this is an example that we've done before, but let's look at it in this formal context. slightly more formal context. So the example is, what is the given probability? What is the probability of a given D set of n being monochromatic when n is red, blue colored? Okay, let's set it up in terms of this discrete probability. So what we need to think about is, what is the set A of all possible events? Okay, so here, A is going to be the set, I like to think of it as pairs. D is going to be your D set, and C is going to be your coloring. So we'll put such that, so D is a subset of n of size little d, and C is a coloring of n. So we get pairs of choose your subset and your coloring of the numbers 1 up to n. Okay, so then what is our set X that we're looking for? So X is, we want to have D be monochromatic, right? So that's going to be the set of X is going to be the pairs D, C, such that the same as above and D is monochromatic. Okay? So does that help us to figure out this probability? So now we know that all we have to do is count this set and then divide them out. So let's see how that works. So this is a pretty easy one to do. And a lot of the examples that we're going to do are easy, but the answers are sometimes insightful. So in this particular case, what's the size of A? Well, how many ways can we choose a D set? Well, by definition, that's n choose D. So that's the number of ways we can choose D. And how many ways can we color the numbers 1 up to n? Well, we have 2 colors, and we're going to pick independently for each of the n letters. So that's it. That's A. What's X? Well, for the size of X, we're going to do something fairly similar, but we now have to be a little careful because D is monochromatic. So let's choose D. That's going to be n, choose D again. We're choosing that D set. And now we need to color D. So 2 choices. It's going to be monochromatic. Everything in the set capital D is going to be colored red or blue. This is my 2 choices of what color to make it. And now I have everything else. So I'm going to have 2 to the n minus D. This is color everything else. And so when I put this all together, I get that the probability of X that we used last time is just going to be the ratio of these. So this is going to be n choose D times 2 to the n minus D plus 1, just combining my 2's there, divided by n choose D, that's why we didn't see it last time, times 2 to the n, which of course agrees with what we had last time, which is 1 over 2 to the D minus 1. So this is a fairly simple idea that we're going to see has lots of really interesting applications.